Okay, got a set of Helmholtz coils here. A bunch of loops of copper wire, wound one way, then wound another way. Actually, they're probably wound the same way, but that's okay. As you've seen, if I crank this thing, I create something that we believe to be an electrical current. So the electrical current goes in here, goes around, comes out here, okay? Now that of course entails an electric field within the wires, and a uniform electric field within these coiled wires. But we'll worry about that later. Just want to demonstrate with this compass that if I crank this thing even a little bit, the compass moves. I crank it one way, it moves one way. Crank it the other way, it moves another way. The compass is acting a little funny. You might be able to get another one in here. Okay, there's apparently a little friction in there, but we're going to get the idea. Going to move this just slightly. That reacts a little better. Okay, so if I continue, if I crank this thing, we see both compasses aligning with the axis. Cranked it too much, right? Well, maybe not. Afraid I'd messed with the magnetization, but that wouldn't have happened. Okay. If I crank in the other direction, of course, the magnetic field is in the opposite direction. The Helmholtz coils, incidentally, there are a bunch of them. They're 10 centimeters, 10 centimeter radius, and 10 centimeters apart. So the distance apart is equal to the radius. It creates a fairly intense magnetic field, especially if you run a lot of current through this thing. I'm just running a little tiny bit of current and still getting quite a response here. So we see that electric field in this direction, or this direction, I can't tell which, creates a magnetic field in this direction. Conversely, a magnetic field in this direction, if you change the orientation of the magnet, if you change the flux, creates an electric field around these things. And they're perpendicular to one another, hence the cross product and the curl and all that stuff. Okay, so there's that demonstration.